Okay, hi everyone. It's 1 minute after 5 p.m. and then we have 8 of you here. Okay, and we can get started. Today's class should be finished like roughly around 1 hour, and then in the past few lectures we have introduced the postulates in quantum mechanics, the 6 of them. We have reviewed them once again last Thursday. So today the focus would be kind of summarize how you can use this postulate to solve quantum mechanical problem in general. Okay, it's kind of like a guidance. And then if you like in this class, the requirement would be if you can apply this to a real quantum mechanical problem, which of course has to be solvable first, then you have no problem with the exam, you have no problem with the homeworks. And then the idea is that actually just understanding the procedure of solving the quantum mechanical system can help you in the future, like if you if you decided that you're interested in taking further advanced quantum mechanical classes. Okay, so just quickly mention again the postulate. One is quantum mechanical system described by wave function. Second is that the amplitude square of the wave function represents the probability of finding the electron between A and B, and then C is the superposition condition. Any two wave functions that belongs to the system and their linear combination that also construct a possible configuration for the quantum system. And the fourth is that for the quantum mechanical system, any physics attribute that you want to measure correspond to an operator. An operator can be a function of x, or differential of x, or even other things. And 5 is that to do a quantum mechanical measurement, for example, if you want to measure A, the measurement result can only be the eigenvalue of the operator A. Okay, and then the eigenvalue is defined in this way. And number 6 is that now given a wave function, and now you want to measure A. Okay, you know the eigenvalues are this, but then what are the probability of measuring specific value, for example, AM, right? And then the way to do that is that you expand your wave function in terms of the eigenfunctions of A, okay? And then the coefficient in the front, the amplitude square, will give you the probability of measuring A at the value AM. And then this is not complete yet, so we have a star here. Later I will say there's a second half of this postulate. And then of course, one final thing is that the entire quantum mechanical system, the motion, is determined by the Schrodinger equation, which we have already introduced 2 weeks ago. Okay, so this is the starting point. And then also last Thursday we introduced the concept of orthogonal, and then we'll use them again and again throughout this class. Now the procedure of solving a quantum mechanical system. A quantum mechanical system can be something like extremely classical. For example, an electron circulating around an atom, right, in the nuclear. And then this one you can solve it classically, and then you will find, okay, it doesn't agree with the experiment, you have to solve it quantum mechanically. So the first step 1 of solving a quantum mechanical, solving a problem in quantum mechanics is to write down the Schrodinger equation. Okay, it's just to write down Schrodinger equation. And in this class, you will only be asked to solve one-dimensional problem. So this is the one-dimensional Schrodinger equation. Differential of t, this is the momentum square divided by 2m. So this is kinetic energy. This is potential energy, and then this is the wave function. So the only difference from one problem to another problem for one-dimensional system is suppose you only have one object, for example, one electron, and this is also true for this class. The only difference would be the potential well, right? For example, if your electron is circulating around a nuclear, then your potential is given by Coulomb's force. And then if your electron or your particle is connected to a string, right, and then you're doing this periodic oscillation like a harmonic oscillator, then your potential energy will also be different. And also you can have a free electron, right? There's no potential energy. The potential energy is 0. So the step 1 is just to write down the potential energy. Okay, this one is fairly straightforward usually. And then because this is a differential equation, right? So to solve a differential equation completely, you have to use boundary conditions and initial conditions. This is what we talked about in the in the lectures of fundamental of waves. And how many, let's see, boundary condition here, and then initial condition. BC is boundary condition, IC is initial condition. So how many boundary conditions do we need? Oh, okay. My apology, the shorting equation is wrong. A little bit embarrassing. Okay, this is the momentum divided by 2m. Yep. Momentum squared divided by 2m. So how many boundary conditions do we need for this Schrodinger equation? Okay, this differential equation has a second order differential on position, so that you need 2 boundary conditions, okay, to eliminate all the free parameters in your solution. Okay, so you need 2 of them for one-dimensional Schrodinger equation. And then for 2-dimensional, of course, it will be partial over partial y squared. So you will have 4 boundary. You will need 4 boundary conditions. For 3-dimension, you need 6 boundary conditions. And then for initial condition, this is something kind of interesting and kind of unexpected for quantum mechanical system, is that the differential on the time is only the first order differential. So you only need the one initial condition, meaning that you only need to know the wave function at time equals t0. Okay, and this is very different from classical mechanics, because classical mechanics, we need to know initially where the particle is, and also we need to know how fast it travels initially, right? So why? Okay. Why in quantum mechanics the condition is reduced, okay? And then you can kind of think is that one way to understand this is actually lies in the Fourier transform, okay? So let's see, in classical case, you need to know initially where it is, and initially what's the velocity. Okay, or the momentum, right? Okay, and then previously when we introduced Fourier transform, we actually know that if you know the wave function, okay, described by position, you can actually apply a Fourier transform to know the wave function in k space, in momentum space. So what it means is that for the quantum mechanical wave function, knowing the initial condition in terms of position actually gives you full information of momentum as well. Okay, as momentum as well. So you only need to know one of them, and then you can automatically know the other one. Okay, so this is the first step, and then for any quantum mechanical problem, you have to write it down to make things a little bit more organized. And then step 2 is that apply the simplest separation of variables to this Schrodinger equation, and then and reduce it to what people call time-independent Schrodinger equation, which is actually just the the equation of the it's just trying to solve the eigenstate and eigenfunction of the energy operator. So what we can see here is that you can take psi xt, and then the notation here is kind of, you have to be a little bit careful. People use the same notation to denote the wave function with x and t, and then just the wave function of x. Okay, and then here is for the eigenstate. This is for the eigenstate. Okay, you can plug it back in, and then you will see that actually, if you plug this back in, what you will see is that the Schrodinger equation will reduce to this time-dependent term will be completely cancelled, and will reduce to will be reduced to like this. And it's very easy to verify because this is the only time operation, and they act on this and give you E in the front. H canceled, I cancel each other, so you got En. Okay, and if you look at this, okay, this is the operator called Hamiltonian. Okay, Hamiltonian, and then this is the, this entire thing is called Hamiltonian. It's just the energy operator. So the energy operator acts on your wave function, giving you a number times the wave function itself, right? So this is simply the eigenstate function, eigenstate equation for the energy operator. But people also call it time-independent Schrodinger equation, which is, I think this is what the textbook call it. Okay. And now, if you come to this step, then this is just a differential equation. And then if your math is good enough, or if you're very skilled in Mathematica, I'm assuming that you can get the result. Okay, solve for psi n. And in this class, you will not be asked to solve any new equations. So all of these systems we teach in this class has been solved by someone like 90 years ago. Okay, so it's kind of not really that meaningful to ask you to redo that process. Okay, but then I would say I really recommend that at least know a little bit of what the solution to expect. For example, if it's a free particle, then it's cosine and sine wave, and then if it's if it is a hydrogen atom, then you can expect a spherical function. And later we'll talk about the harmonic oscillator. Okay, this one will actually give you a very complicated function. Okay. Now we get psi and all the eigenfunctions. And then the third step is to use your postulate 3, right? Postulate 3 tells you that your wave function is a superposition of all possible configurations. And you know that all these eigenfunctions, n could be 1, 2, 3, and keep going. Usually n can be go from 1 to infinity. Okay, usually there are infinite amount of states. So you know that the actual solution per psi xt, okay, the actual solution corresponding to the Schrodinger equation that will satisfy initial condition would be would be a superposition of all these eigenfunctions, right? Because eigenfunctions are possible configurations of Schrödinger equation. We just solve them, and then the superposition of them also is a possible configuration. And let's put this here. And here there's a little bit of trick here, is that alpha n, the coefficient here, is it time dependent or time independent? Okay, and then in this class it will be time independent, just for simplicity. All the example I gave you is actually designed to be time independent. But there's one easy way to kind of see this, is that if you can solve this analytically, really analytically, okay, and you can, well, there's a way to prove that this can be time independent, okay. But then if this is just a proximate solution, okay, it's not the real mathematical eigenstate, then this could be a time dependent term, okay. And we will not go into that detail. Just in this, I just want to bring this up. This might not be time independent in certain cases, and you can kind of keep writing it down, keep expanding this to here, alpha n per psi nx okay. So when you solve the psi n, when you solve this differential equation, you will actually need to use your boundary conditions. That's why you have integer number usually. Okay, and so here what you can anticipate is that this function now has t, and then we haven't used initial condition yet, right? So the next step is, intuitively you can think, okay, then it's to use initial condition to figure out what are the alpha n, okay? So the fourth step, let's see, where do I put it? The fourth step is to use initial condition to solve alpha n. And then here we have to use one conclusion from eigenstates. We haven't proved it here yet, but we'll prove it later today, is that all the eigenstates, they are orthonormal to each other. Okay, so previously, last Thursday we have already showed that, okay, in wave function space, you can define orthogonal in terms of an integer. This is just simply to replicate the inner product in three-dimensional vector, and then assume that you can stretch the dimension from three-dimensional all the way to infinity, and the sum will become integer. Okay, this is how we get the definition for inner product. And then orthogonal is just the same as how we define orthogonal in a vector. Okay, if the inner product of two vectors or dot product of two vectors are 0, then we call them orthonormal. So it's the same here in the wave function. If the inner product of two wave functions come out as 0, then we call them orthogonal to each other. And then so for any eigenstate, okay, for any eigenstate, you can actually show that if they're not the same eigenstate, right? If one is n, the other is m, okay, then they're always orthogonal to each other. It's the integration, the inner product is 0. And then if they're the same, then what you're doing is if they're the same, then you're doing this, right? right? If they're the same, then you're just doing this inner product, which is the same as your postulate 2, right? So this one has to go to 1 because this represents the this represents the probability of finding an electron from minus infinity to infinity, right? So this one has to go to 1. So these two in combine is called orthonormal condition. Okay, they're orthogonal when n not equal to m. So when you're doing inner product of two different eigenfunctions, but they're equal to 1 when you're doing inner product of the same eigenfunctions. Okay. So one thing that you can do is that if you have this condition, and this is something very similar to Fourier transform, then what you can do is that you can write down psi, the wave function you want to solve, okay, and you multiply that with psi m, okay, from minus infinity to infinity. Okay, do this calculation, and what that will give you is it will actually give you the coefficient of when n equals m. Right, so the way to look at this is that, okay, this gives you, so time equals 0. Yeah. Because we know the initial condition, okay, time equals 0. And then for time equals 0, all the psi m, okay, is just psi m itself. Because time is 0 here, this term is 1. Okay. So do this integration. This integration is actually known because you know in initial condition this function is known to you, and you have already solved the eigenstate, so you also know this. Function here. So just do this integration, and then on the right hand side, if you plug in this to here, then what you will see is that the integration is just, okay, psi m star x, and then alpha n, and then psi n. Okay, right now time is equal to 0, so this term is 1. Okay, this term is 1, so we can reduce it to simply to x. Okay, dx. Okay, so this is just expressing this in terms of step 3. Now, we know that you can exchange the order between integral and sum because they're all sum. And then what you can do is that you can get the sum outside n equals to 1 infinity, and then alpha n, and then you get this integration psi m star x psi n x dx. Right, and if you look at this and compare with the top, this is just the orthonormal condition. Right, this is just the orthonormal condition. So this one equals to, so this integration equals to 1 when m equals to, well, when n equals to m, and this integration equals to 0 when n not equal to m, right? So despite you're having from 1 to infinity, you have infinity terms, but only one of the terms is non-zero, right? So this one, when n equals m, it gives you a non-zero result, the only non-zero result, so this is alpha m. Okay, so this is how you get the alpha m by calculating this integration. And this is just like the Fourier transform. Okay, in Fourier transform, what you guys calculate is that if you have a time signal Vt, and now you want to know the frequency signal V omega, then what you do is V omega equals to an integration of Vt e to the minus I omega t dt. Right? This is exactly the same thing. You know your function at initial condition, and then you multiply with the eigenfunction here. Okay, for Fourier transform, this is the eigenfunction. And then you do this integration, and then you get the coefficient for the eigenvalue m, right? Eigenfunction m. In the Fourier transform, then you get the value for frequency omega. Okay, it's the same thing here. Any question to this point?
What's the meaning of the star?
Oh, star is the conjugate, complex conjugate.
And why is that necessary?
So because your Schrodinger equation have complex number, right? So that in general, the wave function will be complex. And then the inner product, when you're doing inner product of yourself, right? It's just vector times itself, inner product of itself, always has to return to a real value, right? If you think about it in a three-dimensional vector, okay? Inner product, if inner product of itself simply means measuring the distance or measuring the magnitude of your vector, right? So for the inner product to return to a real value when n equals to m, right? The easiest way, or actually the only way for it to be true for all wave function is to get a complex conjugate here. Okay, does that make sense? So that this will return to as this, and will always be a real number.
Okay, so like if I'm trying to understand it, are you sort of taking one solution of the wave function and then like saying that, oh, here's like another solution, but if they're the same solution, then we can get a probability at a certain like measurement?
No, so this one, this expression here is the same, mathematically, it's the same as dot product in vector. Okay, because in dot product, if you try to think about it, the dot product is just if A is x1, y1, z1, B is x2, y2, z2, then you get x1, x2 plus y1, y2 plus z1, z2, right? So that's the dot product. And then imagine now if this is not three-dimensional vector, but infinite dimension, then what you do is that you keep writing down, right? Like you can say this is A is x1, x2, x3, all the way down to xn, and keep going. And then B is y1, y2, y3. Keep going. Now A dot product B is just the same dimension, they multiply together, right? So this will give you x1, y1 plus x2, y2, and all the way to infinity, right? So if you look at this and look at that, they are actually the same thing, right? If you write down A, because if you have infinite dimension, right, each value here, psi n x, a specific x, can be interpreted as one of these x here, right? So the idea is psi x can be expressed as psi x1 psi x2, and keep going, right? You can kind of write down your function as a vector with infinite dimension. Okay, so then the sum is just the same as integral, right? Summing all the terms together is the same as doing integration. So that this term simply means an inner product or dot product in vector space. It doesn't have any physical meaning. Okay, this is a mathematical definition.
So I guess that's just the expanded form of amplitude squared is probability?
Yes, it happened to be the probability, but this definition itself has nothing to do with probability. Okay, this is actually, in linear algebra, this is called Hilbert space. It's independent from quantum mechanics. Okay, it just happened that, I forgot which one discovered this first. It's either someone in physics discovered this and then a mathematician proved that, okay, this can be unified with vectors. And then, so this later is integrated into linear algebra and it's called Hilbert space. Okay, so definition here is just an inner product. Okay, just like dot product here. Yeah.
I also had another question
Yeah.
before when you said if you knew the initial condition of the position of the wave function, you also know the momentum, but doesn't that violate the uncertainty principle, or it's like you can't?
Yeah. Yeah, good question. So you don't know the exact value of x and p. You know the wave function. So it's like, so it's like when you measure it, it's still uncertain. But then the wave function describing it is, we know that. That's fine. The uncertainty principle is not saying that you don't know the wave function. It's just saying that when you try to measure it, you can't really measure x and p at the same time. Okay, but theoretically, as long as you get the wave function of x, you can also get the wave function of k. Okay, yeah, very good questions. Yeah, also I encourage you guys to ask lots of questions because, it's like when I first learned quantum mechanics, it's like almost 10 years ago. I have many questions, and then unfortunately at that time, the professor taught us was a little bit intimidating. He was a very famous professor in theoretical physics, and then anything we asked sounds very trivial to him. And then, so we didn't ask a lot of questions. And then I actually later learned quantum mechanics by myself, after that class. So it's a little bit. I kind of understand like the struggle here. Like a lot of this concept are new, and then and the funny thing is that for quantum mechanics, one funny thing is that the way to see whether you really understand quantum mechanics or not is just by listening to your question. Like if someone who haven't taken this class, when they saw this, the question they ask will actually sound very different in terms of language. And this is something true like in conference, quantum conference. And actually because of this, it's a little bit discouraging, especially in national conference or international conference, that many people are not brave enough to ask questions, because immediately people will know that, okay, you're not one of the people in the field. Okay. Okay, so from here, okay, after this fourth step, then what you have already got is that you get the complete solution for psi x and t. Right, you get a complete solution for your Schrodinger equation because you solve all the possible eigenstates, and then by using initial condition, you get all this superposition coefficient here. Right, so you actually have a complete solution for your psi. Okay. Now, after this, then of course the next question in quantum mechanics is that, okay, if I want to measure something, what would I get? Right? Because knowing what the wave function is doesn't necessarily mean that you know the measurement result. And then from an experimental point of view, the measurement result is actually more important, right? Because you have always to, the only way that you know your theory is correct is by comparing your theory prediction for the experiment and the actual measurement from the experiment. Okay, so the next two steps, next four steps are to measure result from this, are to measure a quantity. For example, let's say you want to measure quantity A. Okay, it can be momentum, angular momentum, position. It can be anything as long as it's measurable. And then the first thing to do is to write it down in operator form. And this one, you can try to figure it out by yourself, but then these things has been figured out by numerous physicists, many years ago. So for example, if you want to know what is the angular momentum operator, just Google it, and then Wikipedia will tell you. Okay, and also you can look it up in the textbook. And then if you want to know, okay, how can I get this from a scratch, then we can discuss this later after class. So you write down A as an operator, and now you have to apply postulate 5 and 6, right? Postulate 5 tells you that the measurement result of A can only be the eigenvalue of A. And then postulate 6 tells you that if you express the state in terms of the eigenstates of A, then you can get the probability of getting the result corresponding to AM, right? So by using these two postulates, you can actually get the complete result of the measurement. So here's how you do it. Okay, unfortunately you first have to solve the eigenstate function again. Okay, just like what postulate 5 says. So when solving this, you can use the same boundary condition because the boundary condition imposed on the entire system, right? So you solve this, okay, and then here, at the beginning, people can kind of get confused, right? We say this is the eigenstate, but then this is also eigenstate. Are they the same? Are they different? Or what are they? Right? So the way to understand this is that for each operator, for each operation, you would have a group of unique eigenstates. Right? For example, the eigenstate for position is the delta function, right? It's like you're at position x1, that's your eigenstate. For momentum, you will have a different group of eigenstate. For example, for momentum, it's actually plane wave because plane wave have a fixed momentum, right? And then if you're solving angular momentum, then you will see, okay, the eigenstate is actually a spherical wave because they have a spherical symmetry, just like the momentum, angular momentum is conserved. So for different operator, you will have different eigenstates, okay? And then what is this eigenstate? Right? What is the eigenstate we solve here? These eigenstates are eigenstates of Hamiltonian, right? And then they are very special is because Hamiltonian is directly related to how the state evolve. Right? Hamiltonian is directly used in Schrodinger equation. So Schrodinger equation dictate how the wave function evolve. Okay? So these eigenstates are eigenstates of the Hamiltonian operator. So this has become very simple. If you, after this initial 4 step, if all you want to measure is just the energy, right? Then you can just simply apply postulate 5, okay? Because you already, then A becomes H, right? If you just want to measure energy, then you already get all the eigenstate, and then eigenvalue, and then you already get all the coefficient in postulate 6. so that if you want to measure energy, you can just directly use postulate 5 and 6, okay, without further steps. But in general, okay, we want to measure things other than energy, then you have to solve this eigenstate corresponding to your operator, which corresponds to the physics attribute you want to measure. Okay, so after solving this eigenstate equation, you get all the possible measurement results you can obtain. And then the next step is that, okay, you want to know what are the probability that all these results showing up in the experiment, right? Then here we'll apply step 6 is to express your wave function that you already solved in 3 and 4, okay? To a superposition of eigenstate of A, right? Because only then, when this coefficient will correspond to the probability of measuring A. Right here, in step 3 and 4, the coefficient alpha correspond to the probability of measuring energy, right? Because this eigenstate is the eigenstate of the Hamiltonian, the energy operator. Okay, if you want to measure momentum, then of course the probability is different. You have to calculate it again. Okay, so how do we do this? How do we know beta n? Beta n, again, you use the same trick as step 4. Okay, what you do is that you use the orthonormal condition of the eigenstate. So you apply psi A m conjugate and then x So in general, sometimes operator will depend on time t, but usually they are not. For example, momentum operator is differential of position, and that's it. And angular momentum is r cross type p. Okay, so usually it's not dependent on t, so that their eigenfunction also will not depend on t. Okay, so times psi, your wave function here, xt. And notice that at this point, you already know what your wave function is because you already solved it. Okay, and then dx. And then this integration, you can actually calculate it numerically because you already know this, you already know this. So the net result of this is just a number. Okay, and then the right-hand side, you can write it out using this, and we'll skip a few steps here, but then n equals 1 psi beta n. Yeah, beta n. And then psi integration psi conjugate m x times psi n xt. And then here xt you can decompose it, right? Oh, there's no t. Okay, so psi a m psi a n x dx. Okay, so it's the same as step 4, but then this time you multiply on the left-hand side is the eigenstate of your operator A, and then you do this integration. And on the right-hand side, you can kind of see that this will again be orthonormal condition. This is an inner product between two different eigenstates. Okay, and it might seem a little bit odd. Okay, why all eigenstates are orthonormal to each other? Later we'll prove that. Okay, we'll later prove that today for you guys. And here, then what would happen is that if this is a delta function, well, if this is orthogonal condition, then you know that when n equals to m, the result is 1, and then when n not equal to m, the result is 0. So that this sum also only have one non-zero term, and that's when n equal to m. So this one equal to beta m. Okay, so this is how you get beta m, and then you apply the postulate 6, and then you can get the probability of measurement result as am is beta m amplitude square. Okay, this is just directly using the postulate 6. And one thing we have to kind of pay attention here is that usually when you measure something, you know that the measurement result kind of depends on when you measure it, right? Because the system is evolving with time, it's not steady. So here, when you look at this integration, you see that the left-hand side, psi A, the eigenstate of A is not changing with time, but then the psi, the wave function of the system actually evolve with time. Right? So when you do this integration, the result, okay, the numerical result on this side would be time dependent. Okay, in general would be time dependent. So that means your beta m is also time dependent. Right? So that actually makes a lot of sense, right? If no matter when you measure it, you always get the same measurement result. That means your system is not evolving. Then it's actually quite a boring system because there's no time variation here. Okay. Any questions?
How does the time-dependent psi turn into? Because on that one integral, you have psi conjugate a comma m, and then psi x comma t. But then on the integral right next to it, there is no x comma t. Where did that go?
Yeah, there's no t here, so the t is actually here, inside beta. So that means, because on the left-hand side, the function, after integration, the function, it will be a function of time, right? And then on the right-hand side, you don't see any t term, time term. So the only possible way to resolve this is that your coefficient beta here is not a constant, but instead it's actually a function of time. Okay, so what it means is that you can think about it in this way. Okay, if I'm moving, let's say I'm an electron and I'm moving, okay, on this side. If you want to measure it at this moment, okay, you'll see, okay, I have most probability being here. But then if I, for the next moment, my probability of being there reduced to 0 because I'm already here now, right? So this probability of measuring a certain eigenstate or eigenvalue has to be time dependent. It's actually, well, if it's not time dependent, then it's not physical, right? Because things are evolving with time. Okay. Any other questions? Now, let's talk about the next thing. Okay, it's not complete yet, but so now after this step 5 and 6, you can predict, okay, the probability of measuring A, then what result you will get, the eigenvalues, and what probability you will have to get result am, right, at time t. All is very good. A question I want to pose here is that what would the wave function become immediately after the measurement? Okay. So you'll have your wave function solved by the Schrödinger equation and initial condition, boundary condition, right? So immediately after measurement of A, would the wave function change? Anyone try to make a guess?
Yes.
Yes? Okay, why? Because it doesn't...
Sure.
Yeah, go ahead.
In the beginning, you said something like it collapses.
Yeah, yeah, okay, yeah. So this is actually one of the concepts that was debated for more than 30 years. Okay, it was proposed by, I think it's Max Born, and then Albert Einstein strongly disagree. So Max Born didn't receive a Nobel Prize until Albert Einstein passed away, and then eventually, actually, it's just one interpretation of what happened, but then mathematically it has to go this way. Let's think about this. Okay, let's assume that the wave function does not change after measurement. Okay, let's assume that, because you can kind of see that from a classical mechanics point of view, right? If you if I want to move to the left, then despite whether you see me or not, whether you do a measurement of where I am or not, I'm always moving to this direction. So your measurement doesn't interfere with my existence. Okay, but let's look at here. If the measurement is probability, then there's a problem. Okay, if I measure, let's say there's an electron here. If I do this measurement and then I get result AM, and let's say the wave function doesn't change, and then I immediately after that measurement I did a second measurement which is exactly the same measurement, then what measurement result would I get? You will still get a probability result, right? Because if your wave function haven't changed, and then we know that postulate 5 and postulate 6 is still valid, then you can still get all other possible results with the probability given by alpha. Right? If the wave function doesn't change, then every time you measure the same wave function, you have to have the same probability distribution. Okay, then this moment you can measure at here, and then immediately after that you measure again, it could be there, and then this is not a measurement anymore, right? What is a measurement? Measurement means that you measure it many, many times, it gives you the same number. That's a measurement, right? Like if you put a ruler and then measure what's the height of this whiteboard, you get the same reading. Okay, you get the same reading, and so for quantum mechanics, we of course, because if it evolved with time. Okay, you can't say, okay, if you measure at this moment and then wait a little bit and measure at the next moment, things are the same. You can't say that. But you can say that, okay, after this measurement, if I do the same measurement immediately after that, it has to give me the same result. Otherwise, it's not a measurement. Right? Otherwise, by definition, this is not a measurement. So if you want to make the measurement valid, meaning that immediately after getting AM, you measure again at delta t interval, time interval, and this time interval approach 0, and your result has to be the same. Okay, this is a measurement. By definition, this is a measurement. And the only way that you can guarantee this is that your wave function after the measurement, after measuring result AM, become psi AM. Right? Your wave function becomes the eigenfunction of AM. Then no matter how you measure it, you will only get AM, right? Because this wave function, the linear combination, all the other terms are 0 other than n equals m, right? So when you measure it again, you always get AM back. Okay, and notice that here I have to emphasize that this operation has to, one measurement has to follow the other measurement immediately, right? Because if you don't do that, then the Schrodinger equation is start to do time evolution, right? There's no saying that if you measure my position at this moment and then you measure that again 1 hour later, I would be the same position. There's nothing like this in classical mechanics or quantum mechanics. Okay, the only thing that is guaranteed is that if you measure this, almost at the same time, and you measure it twice, you'll get the same result. That's a definition of the measurement. Okay, so for postulate 6, the second part of the postulate 6, or it's kind of, you can think of it as the natural derivative from postulate 6, is that your wave function immediately after the measurement become psi am if your measurement result is am. Okay, any questions on this? Okay. And then there's one final step, is that, let's see, where can I write it? One final thing is that in some cases we're not interested in measuring individual values here. We're only interested in measuring the average value or expected value. Okay, in a lot of measurement, this is actually the case. So if you want to measure the expected value, this is step 8. Okay, this is step 7. The wave function collapse into the eigenfunction of your eigenvalue. And then step 8 is the expected value. Later we'll define, okay, mathematically what we mean by expected value. If you only want to measure that, then it's much simpler. Okay, you just your operator A multiply the wave function. Wave function is solved here, and then also times the complex conjugate of the wave function and do the integration from -infinity to infinity. Okay, later we will actually derive this equation. Okay, so it actually took a little bit longer than I thought. Any questions regarding this this procedure on how to solve quantum problems?
Can you go over why you do that step off of the arrow in step 6? So I can't understand how you're trying to find, I guess, beta, which is the probability of measuring a certain eigenstate that you got from step 5, and then is the summation there because you're trying to? Yeah, why is the summation there?
You mean this one?
Yeah.
This is apply the postulate 3.
Okay.
Right, because your wave function, you can always decompose that into a superposition of all possible wave functions. And you already solved this, the eigenstate equation, right? You get all this eigenstate. Then when you express your wave function in regard to your eigenstates of A, then it has to be a sum. And if you can think about this, is that, okay, if there's, for example, if component 1, the first eigenstate, is not part of your wave function, then what will happen is that you would get beta 1 equal to 0. Right? So it's like a Fourier transform thing. You do Fourier transform, it doesn't mean that at every frequency you get non-zero. But then, for simplicity, you still just calculate the entire thing, the Fourier transform. And then you look at the result, okay, there are several peaks, and then those are the frequency of this signal.
Okay, so it's kind of like you're trying to find all the eigenstates that you care about.
Yeah, yeah. Like when you next calculate this, you will see the weight. Okay, in all these eigenstate, they're not equally distributed. Some values would be have higher probability of measuring it.
Okay, and then after the error, how do you get from before the error to after the error?
You mean which part? The here or here?
In step 6, right after the beta assign a comma n.
Mm-hmm.
How do
So
you go from the summation to that integral? Because it's not immediately obvious where beta goes in that integral.
oh, because beta is not position dependent. Beta is time dependent. So and then the integration is only integration of position, right? So this beta can come out.
But then in the integral before that, see there's an equal sign, and then you have another integral before.
Yeah, so this part you're just substituting here. You're substituting this into here. Right, psi equals to sum of this, and then you substitute here, and then you have integral, sum, and beta, right? And we know that you can change the order between sum and integral, right? Because basically they're all just sum. And then you see that the integral is on position x, while beta is not a function of x, so that the beta can come out of the integral.
Oh, okay. So, right. So that's a separate. That's a separate equation that you brought in.
Yeah. Yes. Yeah. Brought in from here. Yeah. Yeah.
Okay.
Yeah. Okay. Yeah. I mean, next week we will actually show you guys the simplest example in quantum mechanics that apply all this procedure, and then you will do homework, and practice all this. And then right now it would be a little bit confusing because it's all just, these are just equations. There's no examples here. There's no system here. It's very, yeah. Okay. So we have 10 minutes left, and let me try to decide what to talk next. Yes, okay. One thing that, now we'll talk about let me erase this. Any other questions? By the way, after this, you guys can actually rewatch some of the, tech movies, and then try to see whether those claims are accurate or not. For example, I don't know if you guys are too young to watch the Big Bang Theory. It's a TV episode about a few scientists in Caltech. At least I'm a big fan because I'm from Caltech. And then there's an episode saying that Sheldon, the main character, is struggled with the equation. And then the punchline is that at the end of the episode, he shouted out that, I did it wrong all the way. The electron is a wave, and I treat it like a particle. And I was like, well, Sheldon is almost a professor, and then he's trying to solve electron. He should know that the first thing to do is Schrodinger equation instead of treating the electron as a particle. And actually the net result is that you can't watch science fiction anymore. Like there are many science fiction books my wife is very interested in, and then usually after the first few pages, I have to turn it down. I start to nitpick all the problems. Okay. Now, one final thing of today is that we'll have to carry on with this discussion regarding some technical details in this procedure. But one thing here I want to emphasize is that the operator A. okay, the operator A of a physical attribute or something that you can measure. Okay, and if you look at the postulate, it says that all the possible result of the measurement is given by your eigenvalue. Okay, eigenvalue. And then we know that in the measurement result can only be a real value, right? It cannot be a complex number. It has to be a real number. So an has to belong to a real number. Okay, and this should give us some limitation or restriction on operator A, right? Because not all operators give you a real eigenvalue. Some operator will give you, complex eigenvalues, right? So now let's see if the eigenvalue has to be real, then what is the constraint for the operator? And this is called, the short conclusion is that the operator of any measurable physics quantity has to be a Hermitian operator or self-adjoint operator. So Hermitian is actually a word you will hear a lot if you go to quantum mechanics or any quantum-related conference. And I'll quickly prove to you guys, okay, what is Hermitian or what is self-adjoint and why it gives us a real eigenvalue. So the definition of self-adjoint, if you go to page 30 on the lecture note, it's actually written there. I'll just read out the inner product. Okay, inner product between A psi 1. Psi 1 is an it's just a wave function. It can be any wave function. The inner product between A psi n, psi 1 and psi 2, okay, inner product of this is equal to the inner product of psi 1 and a dagger psi 2. Okay, and this is a dagger is the adjoint operator of A. Okay, so this is a mathematical definition. Okay, there's no physical meaning, a mathematical operation. For an operator, if you can find another operator that, okay, make this the same, this inner product of this equal to this, then this is called the adjoint operator of A. Okay, and then in linear algebra, if this is a finite dimension, okay, for example, a vector, you can have 3 dimension, 10 dimension. As long as it's finite, then A would be a matrix, right? Because this is a vector now. Then anything operate on a vector is actually a matrix. And you can show that this is in linear algebra, this A dagger is the complex conjugate transpose of A. Okay, in linear algebra, in matrix, this is how people use dagger here. But then if this is infinite dimension, for example, for the momentum operator, position operator, and angular momentum operator, you can't say complex conjugate transpose because it's not a matrix. It's infinite. It's a continuous infinite dimension. Okay, and then self-adjoint by the name is now very clear. Okay, is that if the adjoint operator equals to the operator itself, then it's self-adjoint. Okay, this is a definition. Physics, mathematics definition doesn't have any physics meaning. Now let's see how this self-adjoint. So in mathematics it's called self-adjoint. In physics it's called Hermitian. Okay, they're the same thing. So now let's quickly see that how the self-adjoint can lead to a real eigenvalue. Okay, all the self-adjoint operator has real eigenvalue, and if we use this definition, meaning that adjoint means that the inner product of A per psi 1 and per psi 2, right? This is A per psi 1, this is per psi 2, and then you do inner product. Inner product, you need to have a complex conjugate here. This is what we just said. Equal to, by definition, self-adjoint means per psi 1, the inner product of these two, A dagger per psi 2 dx. Okay, this is the definition of adjoint. And then now because you're self-adjoint, so A dagger equal to A, okay, you'll have this. So this is the definition of self-adjoint. Okay, this is definition. And it's interesting is that when you ask mathematician why you define things this way, they usually say, okay, they usually don't answer your question, just say, this is the definition. And now let's see how we can use this to show you that all the eigenvalues is real number. Okay, one thing you can do is that you can now replace per psi 1, because per psi 1 can be any wave function. Okay, so let's say we replace it with per psi n. N is the nth eigenstate of A. And then we replace per psi 2 also with n, right? Because it's any wave function, so we can actually choose per psi 1 equal to per psi 2, and this equation still holds. All right, so let's do that. N, and then n. Okay, now if you look at the right-hand side, how you calculate this, you see that, okay, A has to act on per psi n. And because per psi n is an eigenstate, so A act on per psi n will give you an per psi n. Okay, so the right-hand side would be an per psi n star an per psi n dx. Right, and then an is just a number, so you put it in the front. Okay, and then you do this integration. This is just normalized condition, right? This will equal to an per psi minus. And then we know that for all the wave function, it has to be well normalized. So this one is 1, so equal to an. Okay, so let's look at the right-hand side. Again, if you have A act on per psi n, it will give you an per psi n, right? So the right-hand side is an per psi n, but then you have to do a conjugate per psi n dx. Right, so if you do the conjugate, then what will happen is that it's now a conjugate coming out. Okay, and then per psi n is just the same as this term. So the left-hand side will become an. Okay. So now you see that for self-adjoint operator, you can easily derive that the eigenvalue of the self-adjoint operator has its equal to its own conjugate, complex conjugate. So this means that it has to be a real number, right? Because only a real number has complex conjugate equal to itself. Okay, so so this is a big conclusion that all the operator corresponding to measurable physics quantities has to be Hermitian or has to be self-adjoint. If your operator is not measurable, then it doesn't matter. Okay, it can be complex number. The it doesn't have to be Hermitian, and it can have complex eigenvalue, because you can't measure it, then the complex number doesn't violate anything. Okay, and that is all for today. And then starting from next class, we will start to talk about the simplest quantum mechanics problem that you can solve, that's quantum well, and then it's actually quite useful because nowadays there are some lasers still use quantum well. Okay, and then I will stay here for a few more minutes to answer your questions.